Hi again, everybody. Today's presentation covers the periodic table. We'll discuss the historical development of the periodic table, its arrangement, and the reasons why the elements are placed the way that they're placed on the table. The development of the periodic table was one of the important events which really turned chemistry into a science. Before that, we had this loose body of knowledge which was called alchemy. Alchemy was pretty great. The alchemists were convinced that they were going to take inexpensive materials like lead and turn them into gold and become rich by doing that process. Now, they were never able to figure that out. However, they did learn a lot about the behavior of many of the different chemical substances and elements. Now, imagine trying to learn a subject where all of the information was haphazard, it was random, there were no rules, no organization. It would be a disaster. So the periodic table actually gave us a way of organizing the elements so that we can learn a lot of chemistry with less time investment. This was Mendeleevs' true genius, to organize the elements into a table based on their reactivity and atomic mass. Another key thing which Mendeleev did, which was super important, was that he left open spaces in his periodic table. One of the blank spaces that Mendeleev left on the periodic table was directly below aluminum. Mendeleev predicted that there should be an element in this spot. He called it aluminium, and he was publishing this information in 1871. In 1875, the element gallium was discovered, and its properties matched up very closely with what Mendeleev had predicted for aluminium. Mendeleev's periodic table was not without its problems despite its predictive power. So an improvement was made to the periodic table by Henry Moseley. Moseley recognized that the problems with Mendeleev's table could be fixed by arranging the elements by their atomic number, by the number of protons, rather than the atomic mass. So there were a few problems with Mendeleev's table. Moseley's rearrangement of the table based on atomic number, based on number of protons, did resolve these problems. One of the important terms we'll use associated with the periodic table is families or groups. This is referring to the elements which are in the same vertical column. We'll call them a family or a group. All of the elements within a family or group will have the same number of valence electrons, I guess with the exception of the noble gases. There is an exception there. They will also have similar reactivity. Let's take a look at an example of this. One example of a family or a group on the periodic table would be the alkali metals. These would include lithium, sodium, potassium, rubidium, cesium, and francium. Hydrogen will have some properties that it shares with the alkali metals, but for some reasons it's not considered to be an alkali metal. The alkali metals will all have one valence electron, and they will react in similar ways. For example, lithium, sodium, potassium, all of these elements, if we put them into water, they will react to form a basic solution, and along with that, hydrogen gas will be produced, which will eventually ignite or explode. A period on the periodic table refers to a horizontal row. Elements that are found in the same period as each other will have the same N, principal energy level. They will have valence electrons at the same energy level. Let's take a look at the periodic table and review what a period means. So again, a period means a horizontal row on the periodic table. For example, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon all belong to the second period. Periodic law refers to the predictive power given to us by the periodic table. What was discovered was this: when elements are arranged in order of increasing atomic number, there would be a periodic repetition of properties of the elements. And again, this would occur within the same column or the same group or family. So if we have an element with certain properties, later in the periodic table we're going to find another element that's going to have very similar properties to this. Not identical, but similar. We saw an example of this in the short video where they were trying to generate element 114 because they were predicting that it would have properties similar to lead. Periodic trends refer to properties that are found in repeating patterns within the periodic table. Some examples of periodic trends would include atomic radius, electronegativity, and ionization energy. For example, similarities in reactivity. We know that the noble gases don't typically react chemically. Another example of similarities in reactivity would be found within the oxygen family. We know that oxygen will react with hydrogen to form water, H2O, combining in a 2-to-1 ratio, hydrogen to oxygen. Sulfur is going to react with hydrogen in a very similar manner, forming hydrogen sulfide, H2S. Selenium will react with hydrogen to form, again, a hydrogen to selenium ratio of 2-to-1. And we'll see this pattern continue down the oxygen family. The reason for this is that all of these elements, oxygen, sulfur, and selenium, have 6 valence electrons. Oxygen 2s2, 2p4. There are 6 electrons in the second energy level. For sulfur, there are 6 electrons in the third energy level. For selenium, 4s2, 4p4, there are 6 electrons in the fourth energy level. This means that these elements have the ability to form 2 covalent bonds. So when they're reacting with hydrogen, they'll form 2 single bonds, and that's why these compounds form them in the way that they do. A future video presentation will take a closer look at other periodic trends, including ionization energy, electronegativity, atomic radius, ionic radius, electron affinity, and reactivity. These are some examples of important groups within the periodic table. The alkali metals will be referred to as group 1, the alkaline earth metals as group 2, the chalcogens is the oxygen family. This name is not commonly used. Halogens are group 7, and the noble gases are group 8. Let's take a look at the periodic table again to review these different groups. The Webb Elements periodic table uses the IUPAC system of numbering the groups on the periodic table with the numbers 1 through 18. An alternate system uses a different way of labeling the representative elements. These are the elements that are part of the S block and the P block. So the group 1 on the IUPAC can also be called sometimes group 1A. The alkaline earth metals right here labeled group 2A. Then we skip over the transition metals. We find the boron family. This would be group 3A. The carbon family is group 4A. The nitrogen family, group 5A. The oxygen family, or the chalcogens, group 6A. The halogens under fluorine, group 7A. And the noble gases are group 8A. The strength of this system is that the Roman numeral prefix will tell us the number of valence electrons that any given representative element will have. For example, group 1A elements will all have 1 valence electron. Group 3A elements have 3 valence electrons. Group 7A elements have 7 valence electrons. There is one exception to this rule. It's helium. Helium has just 2 valence electrons because it only has the 2 electrons in the 1s orbital. Let's take a closer look at groups 1, 2, 3, and 4. Group 1 is the alkali metals, or group 1A. They will have electron configurations that end S1. I like to help myself to remember this because the alkali name ends in a single I. That is the Roman numeral 1. So I always remember that alkali metals are group 1. Group 2 are the alkaline earth metals. They will have 2 valence electrons. All of these metals are extremely reactive, so when we find them in nature, they'll be part of compounds. The boron family, group 3A, will have 3 valence electrons. Boron is considered to be a metalloid or a semi-metal. The other members of this family are considered to be metals. Aluminum is considered to be a light metal, and it has quite a bit of significance because of its uses for producing things like aluminum cans for beverage storage. The carbon family is group 4. We would predict an electron arrangement like this. However, what happens is that the orbitals will actually hybridize, forming this arrangement, S1p3. This actually makes it possible for elements like carbon to form 4 bonds, and this is one of the factors which caused carbon to be the element that life is based on, because carbon has so much flexibility in its bonding. It will form tetrahedral or four-sided compounds. We also know that tin and lead are very important metals in here. Lead used to be used quite a bit for plumbing. Actually, that's where it gets its symbol. Pb is from the Latin name plumbum, which is the Latin name for lead. Now, because we know that lead can cause toxicity, lead poisoning, its uses have been reduced greatly. Now let's take a look at groups 5 through 8. Group 5 is the nitrogen family. These elements will have 5 valence electrons. We know that nitrogen is relatively inactive, however, it will form many important compounds. Arsenic is a very poisonous substance. In the oxygen family, we'll find 6 valence electrons. We know that oxygen is very, very reactive and will react with nearly every element found on the periodic table. The other elements located within this family are going to be less reactive, and they become less reactive as you move down the family. The halogen family will have 7 valence electrons. These are extremely reactive elements. Finally, the noble gases, group 8, will have 8 valence electrons, again with the exception of helium, which has only 2. These were used to be called the inert gases because we used to think that they wouldn't react at all with other elements. It's now known that you can form compounds with noble gases, but it takes extremely high energies in order to get the noble gases to form compounds with other elements. Some other key information about the elements. We know that most elements are solid. Most elements are metallic. Most elements are going to form compounds with oxygen. And most elements are going to be groups of single atoms, monoatomic, in their elemental state. There are a few elements which will be liquid in their pure state. This includes bromine and mercury. On the periodic table that's in the classroom, you'll note that bromine and mercury's symbols are written in blue to indicate this. Cesium and gallium are solids at room temperature, but if you were to hold them into the palm of your hand, they would actually melt and form a liquid because they have very low melting temperatures. There are 11 elemental gases, including hydrogen, helium, nitrogen, oxygen, fluorine, neon, chlorine, argon, krypton, xenon, and radon. And there are 7 elements which will occur in pairs when they're in their elemental state. We call these the diatomic elements. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These are always going to be found in pairs. A mnemonic, to help you to remember this, is BRIF-CLONE. BRIFCLOHN. This is a list that all chemistry students will need to memorize. Let's take a look at a few different alternate periodic tables. There are other ways to arrange the elements. Note the main difference of this periodic table is that the F block is included within the body of the periodic table. It's not typically printed like this because it doesn't fit very well on a single sheet of paper. So the F block is pulled out and placed down below. But this is maybe a more accurate depiction of how those elements are really arranged. Here's an interesting spiral arrangement of the elements. We can start at element 1, hydrogen, and work our way out through the spiral, noticing that we're moving through this area for the transition metals. Then we have the lanthanides and the actinides, and we can see that beyond the elements that we have, 112, 113, 114, we can see that there are actually some interesting predictions about what super heavy elements may look like, what properties they may have. This is the Tarantola periodic table. So noticing here that we're just moving around, placing the F block here, D here, P here, and S over on the far right-hand side. This triangle arrangement is another way of looking at the elements, and we can see that we have, if we follow a diagonal line, we can see a family or a group. Here's hydrogen, lithium, sodium, potassium, rubidium, cesium. So moving down group 1A. Here, moving down through the noble gases, helium, neon, argon, krypton, xenon, and radon. And last but not least, I couldn't resist, I had to put this one in. Here we have the periodic table of rejected elements. So I'll give you all just a little bit of time to enjoy this one. And I'm running out of time, but I have to mention this website. It's awesome. It's ptable.com. You can click on properties and pull up information about the different elements. You can click on orbitals. You can